How do you interpret these confidence intervals? Let's start with what they're not. It does not imply that 95% of the population values lie between these limits. So if it's a confidence interval on infant weights, it doesn't mean that 95% of infants have a weight within those bounds. Is that, everyone believe me? Yeah, because this is a sampling distribution, not a population distribution. It's a really common misconception about confidence intervals. And it does not account for bias in the point estimate, either due to your sampling procedure or a measurement bias. This is only variability due to sampling. So it means that if you were to draw another sample of the same size, you would get a somewhat different estimate. And that's the kind of variability that confidence intervals account for. What it does do is it provides an interval within which we're 95% confident that the true population mean lies, or alternatively, if you were to repeat your experiment 20 times, then approximately 19 times, the confidence interval that you calculate would contain the true population mean. So really, if you repeated your experiment many times, 95% of the time, your 95% confidence interval should contain your true mean. If we calculated a 99% confidence interval, then 99 times out of 100, you should capture the true mean in that interval. So in all of this, that population mean is assumed to be fixed but unknown. So the population mean itself, it doesn't have error to it. It's just like that is the true average birth weight of all infants. There's no error in that, but we don't know what it is. So what this confidence interval does is represents our uncertainty in what that true value is. That can be a bit of a hard concept to get your mind around. We're estimating something that is a single fixed value. There's no error on it, but it's our knowledge of what it is that has error. This is a so-called frequentist interpretation of confidence intervals, the fact that there is one single true value. If you asked the Bayesian, they would have a different interpretation of it, but this is what I tend to adhere to and what we do in this class. So, and if we took repeated samples and constructed the 95% confidence interval around every one of them, then 19 out of 20 times those intervals would contain that true mean, and the other 5% would not. This is just a pictorial representation of that. So this is a simulation where samples are drawn from a normally distributed population of mean mu, and we're drawing repeated samples and calculating a 95% confidence interval from them. And the ones in black cross the correct mean, and the ones in red do not. And you'll see that the size of them changes some because we're estimating the standard error from the sample. So in some samples, you'll get a greater standard deviation, and in some, you'll get less. So they're not all the same size, and they also don't all have the same mean. But 19 times out of 20, this true mean is contained within that interval. That's what's important about the 95% confidence interval. So keep that in mind when you are reading and interpreting about a confidence interval or calculating them yourself, that the exact values that you observe, those are not truth. They're based on a sample. So there's, even if you did your experiment exactly the same way again, but drew a different sample, both your width and the center of your confidence interval would change, which is part of why I don't support reporting too many decimal places in these things, because the decimal places, beyond maybe 1 decimal place, depending on what your sample size and accuracy is. Certainly reporting a bunch of decimal places on your margin of error doesn't make sense, because it's just not, it's not something that you have that kind of a certainty in. It's subject to sampling variability. It's hard to remember when you just put like a whole bunch of your life into collecting a data set, analyzing it, and all of this, to think that, the p-values and the confidence intervals and the point estimates, none of those are like the truth. Like, they're just an estimate based on one sample, and if you did it again, you get different values. But the thing that we count on, if we do everything correctly, is that 19 times out of 20, this confidence interval will contain the true population mean, even though we can't be sure about the point estimate or the bounds of it. Let's do some Q&A. I'll do the questions, you do the answers. So is a 99% confidence interval larger or smaller than a 95% confidence interval? Put up your hand. Let's see, someone new. Okay. Oh, you haven't put up your hand before. What do you think? It's larger? You want to explain why? That's okay. That's okay. Audrey, you want to try?
Sure. I think it's larger because, well, it's 2.58 times standard error.
That's cheating.
But it's larger because in order to capture more certainty, more values.
Yeah, in order to capture more certainty in what the true population mean is, you need more values within your interval. Does anyone have another explanation? Yep.
Can you go back to the picture with the equals crossing?
Yep.
Okay, so for 95% confidence, there are 6 red ones up there. Let's just say there are 5.
Yep.
So for 99%, there would only be 1 red one. So that means the interval has to be wide enough to capture all those.
Very good.
More black ones.
Yep. Yeah, so we have like, I don't know, 6 or something red ones that did not capture the true population mean. If you wanted, and so every 5 out of 100 here is not capturing the correct mean. If you want to increase that or take that down to only 1 out of 100, then they need to be bigger, because the center of them isn't going to change just by changing the degree of confidence. Very good. Any other thoughts about that or other ways of looking at it? I'm impressed, because at the beginning of class, I suspect, and if you went out into the general population, most people would get this first question wrong. Like, and I don't want to say why, because I might confuse you again. But 99%, it sounds like you have more confidence. So why is your interval bigger if you have more confidence? It is. So the second question is, the size of a confidence interval increases, does the confidence increase or decrease? This is kind of the same question. As the size of the interval increases, does that mean that the level of confidence increases or decreases? What's that? It increases, right. That's sound a little funky? Yeah.
I mean, you're sure that most of the times, 99 times out of 100, your point value will be within.
Right. Yep. So you could have two confidence intervals of different widths if they came from different samples. So I'm saying if our information, our data are fixed, and if we adjust the confidence level or adjust the size of the interval around it, does our confidence in the true mean increase or decrease? This is one that really trips people up, because if you think about, if you're really confident, then you should have some really narrow range, right? But the thing is here that the information is fixed. So if you put a small range around it, you can't be very confident in that. But if you put a really big range, you can be very confident that the truth is found in that range. How about this one? As the sample size increases, does the 95% confidence interval increase or decrease? Yep. It will increase? Why? Decrease. Why is that?
Because when you have a larger sample, you more close to the real value. So most of the value will be concentrated.
When you have a larger sample, you get closer to the real value of the mean. Your standard error will.
Yeah.
I think you're on it. Let's hear another answer. Yeah.
So if your n increases, the sample increases, you will instead of going for the false calculating confidence interval, you have to take a specific sample.
Yeah.
So I was like, sample size. I think it should not cause much effect.
It will affect it.
But it will be on negative side, decrease.
Yeah. I don't know. Any more? Yeah.
So the standard error is the standard deviation of population over the square root of the sample size, right? So if any increases, the denominator is increasing,
Yep.
the standard error will decrease. So
That's right.
You're adding subtracting a smaller amount of your weight estimate when you're creating your confidence interval. So the width of the interval will increase, but then your estimate of the population mean will be better.
Yeah, so here's someone with a very mathematical mind. In terms of the formulas, that's exactly correct. Your standard deviation your standard error is the standard deviation over square root of n. So as n gets larger, standard error gets smaller. And as standard error gets smaller, your margin of error gets smaller. Yes?
I mean, I agree with that on average, but you could have two samples, and even the smaller sample you just happen by chance have less variability.
Right.
The larger sample you have values.
Yeah, so the point is that there is sampling variability in the individuals you draw and the standard deviation that you estimate. And so even for a smaller sample size, you might just happen to draw, say, n equals 4 people who are very similar to each other. And for that sample, you could end up with a smaller estimated confidence interval. And that is true. There can be, if you draw enough samples, you will observe a great deal of variation between those samples. On average, if you draw larger samples, you'll have smaller margins of error and smaller confidence intervals. So, but you're right that for any two particular samples, you can't say in advance what standard error you would estimate from them.
Unless you can ensure that the sample is representative of the population.
Even if your sample is completely representative of the population, you will have sampling error. So we're making that assumption here that this sample is a simple random sample that is representative of the population. But just the fact that you're not observing the whole population, you're observing only a few individuals, you could happen to draw the shortest people in the population on one particular draw, not because of any shortcoming of your sampling method. Even if everyone has the same probability of being sampled, you will still end up with some samples of all short people or some samples of all tall people, or samples with great variability within that sample. That's random sampling error.
If the sample is equal to the population, the confidence interval is limited to 0.
Sorry?
If the sample is equal to the population that we are studying.
What do you mean the sample is equal to the population?
We don't have the sample, we have the population.
Okay, we have the population, yeah.
So
Yeah.
the confidence interval is close to 0.
If you have the entire population, then the confidence interval is meaningless. You don't need to put any uncertainty around your point calculation. You know exactly what the population mean is then. Yeah, this is only to represent sampling variability. Good question. One other case where this would be strictly true is if the standard deviation is known from the population, if you're not estimating it from the sample, which is one of the cases where we will use the z-distribution. So you're using your point estimate, the average from the sample, but you're using an already known standard deviation. In that case, then standard error and the width of the confidence interval would strictly increase with n. Okay, last one. What does the confidence interval tell us about variability of individuals in the population? If all you have is a confidence interval, what does that tell you about the variabilities of individuals? Let's see. Yeah. Yeah. Basically nothing, yeah. If you knew the sample size, then it would tell you something, but you could get that same standard error from a whole range of combinations of standard deviation and sample size. So it doesn't tell you anything about variability of individuals. Another very common misconception about confidence intervals. All of these Q&As are based on questions I've asked on previous exams that a lot of people got wrong. So I'm not trying to trick you. I'm not going to go through this example, but it's here for you to look at and just to give you an idea of some of the kinds of calculations that I think you should be able to do. There's a link to a mini tutorial that I made here that's on YouTube, and I linked to it also from the